So let's say I have a predicate, p of x. Remember that as soon as I write there exists an x, p of x, this predicate here, this was a function. It took some input and it output true or false. Now I've written there exists an x, p of x. This has a value. It's either true or it's false. If there's an x that makes p of x true, and we've specified the domain, then it's true. If for every element in the domain p of x is false, then this statement is false. So there exists x, p of x is either true or false. Similarly, when I write for all x, p of x, this is now either true or false. As soon as you add these quantifiers in front of the predicates, you change it from a predicate itself, you change it to something that is just either true or false. Okay, so let's assume that I have written p of x, or let's write p of x as x is even, and let's write another predicate, q of x, where x is odd. And let's say the domain is positive integers. Okay, so how about the following? There exists an x, p of x. Okay, this is true, right? For example, p of 4. How about there exists an x, q of x? This is also true, p of 3. What about there exists an x, p of x, and there exists an x, q of x? Well, this is true. There exists an x, p of x is true, and there exists x, q of x is true. And as we saw last time when we were dealing with Boolean formulas, true and true is true, so this is true. But how about this? There exists an x such that p of x and q of x. Is this true? No, this is false. Why? Is there a positive integer that is even and odd? No. So be careful here. You can't always distribute the existential quantifier. You might think, oh, I can distribute this existential quantifier and get there exists x p of x and there exists x q of x. You might think, oh, this is sort of logically equivalent to this statement, but that would be false. On the other hand, let's say that you've written the expression for all x, p of x, and q of x. It turns out this is logically equivalent to for all x, p of x, and for all x, q of x. You can think about this on your own, or you can ask me in class why this is true. It's also explained in the Rosen book, and I'll be happy to go over it. There's some other interesting expressions that we might want to look at, mainly involving the negation symbol. And these are called De Morgan's laws for quantifiers. So, we were looking at there exists x, p of x. What happens if we want to negate this statement? We want to say it is not the case that there exists x, p of x. Well, this is logically equivalent to for every x, p of x is false, right? If it's not the case that there exists an x for which p is true, it means that for every x, p of x must be false. And similarly, if we want to negate the statement that for all x, p of x is true, that's logically equivalent to there exists an x such that p of x is false. Okay, just the way we had De Morgan's laws when working with Boolean formulas, we have De Morgan's laws when we're working with quantifiers. Let's let p of x and q of x be predicates. Here's some notation we haven't seen before. We're going to be interested in the question, is it the case that for every x, p of x implies q of x. This right arrow here is read implies. I like to think of this as saying the following. Is it the case that for every x, if p of x is true, then q of x is true? Or is it the case that for every x in the domain, whenever p of x is true, q of x is true? If so, this statement is true. For example, let's let p of x be x is odd, and q of x be the statement, the predicate, x plus 1 is even. Okay, and let's let our domain be positive integers. Now the question is this statement true? Is it the case that for every x, whenever p of x is true, q of x is true? Well, yes. If p of x is true, it means that x is odd. So therefore, when we add 1 to it, it's going to flip and it's going to become even. So whenever p of x is true, q of x is true. Therefore, for all x, p of x does imply q of x. Let's look at two other predicates. How about p of x is an integer, and q of x is x squared is odd. Okay, is it the case that for every x, p of x implies q of x? This is false. For example, take x to be 9. So p of 9 is true, and q of 9 is also true, right? Because 81 is also odd. But how about this? P of 4 is true. 4 is an integer. But q of 4 is false. 16, 4 squared, is not odd. So it is not the case that whenever p is true, q is true. Because here we have an example where p is true, but q is false. Okay, so when we're looking at the truth value of this statement for all x, p of x implies q of x, it might be also convenient to understand, when it's false. So if it's not the case that for all x, p of x implies q of x, this is the same or logically equivalent to writing that there exists an x such that p of x is true and q of x is false. So, if this statement, let's say it's true, okay, that's fine. But if it's false, it means that there exists an x such that p of x is true and q of x is false.